All right, today we are cracking one of the most fundamental codes in all of organic chemistry. We're talking about how to react with benzene, this incredibly stable, almost stubborn molecule. You know, you can almost think of benzene as a fortress. It's got this perfect, super stable ring of electrons that basically protects it from most chemical attacks. It is perfectly happy just the way it is. So the big question for chemists has always been, how do we get inside? How do we actually modify it? That's the puzzle we're going to solve.
So let's start by really digging into why benzene is such a tough nut to crack. I mean, it's not like other molecules that have double bonds. It plays by a completely different and way more stable set of rules.
The secret, the magic word here, is aromaticity. And no, this has nothing to do with how it smells, it's a special kind of electronic stability. Benzene has this cloud of electrons that are shared across the entire ring, and that makes it exceptionally stable. Breaking that aromaticity costs a ton of energy, which is exactly why benzene just shrugs off reactions that would tear other molecules to pieces.
Okay, so to get past this incredible defense, we need a special kind of attacker. We need an electrophile. The name really says it all: electro for electron, phile for lover. It's a molecule that is just desperately seeking electrons. And where's a fantastic place to find a bunch of electrons? Well, in that super dense, stable cloud sitting in the benzene ring. This is our key to the fortress.
So, if a direct, brute force assault isn't going to work, chemists develop something more like a secret handshake. It's a universal mechanism that lets the electrophile get what it wants without completely destroying the fortress for good. And this whole process happens in just two steps. First, the electrophile attacks, and for a very brief moment, it actually breaks that cherished aromaticity. This is the hard part. It's the slow step that dictates the speed for the whole reaction. Then, in a super fast second step, a base comes along, plucks off a hydrogen atom, and snap, the stable aromatic ring pops right back into place, but now with a new group attached. Now, that unstable thing in the middle, it has a name, the rhenium ion. It's got a positive charge because it had to use some of its own ring electrons to make a new bond with the electrophile. Losing its aromaticity makes it really unstable, for sure, but it's not totally helpless. It uses this amazing trick called resonance. You can think of it like juggling the positive charge around to different atoms in the ring. This spreads out the instability, helping it hold on just long enough for that second step to happen.
You know, an energy diagram for this reaction tells the story perfectly. You see the reactants starting down here at a low, stable energy level. To get the reaction going, they have to climb this big energy hill, that's that slow first step, to form the unstable rhenium ion, which is sitting right at the peak. From there, though, it's a really quick and easy slide downhill to the final product, which is often even more stable than the benzene we started with.
Okay, so we've figured out how to add one thing to benzene, but what happens if there's already a group on the ring? Well, this is where it gets really, really clever. The ring is no longer a blank slate.
The group that's already attached, it basically acts like a movie director. It controls the entire scene. It tells the next electrophile that comes along two crucial things. One, how fast to react, and two, exactly which seats on the ring, which positions, are open for business.
And these directors, they fall into two main categories. Over on the left, we have activating groups. These guys donate electron density into the ring, making it even more attractive to electrophiles, and, you guessed it, speeding up the reaction. They direct new groups to the spots right next door, we call that ortho, or directly across the ring, which we call para. Then on the right, you've got the deactivating groups. They do the opposite. They pull electron density out of the ring, which slows the reaction down, and they direct new groups to the positions in between, called meta.
So why do activators direct to ortho and para? Well, it all comes back to stabilizing that intermediate ion we talked about. When the electrophile attacks at the ortho or para position, the activating group can directly help stabilize that positive charge through resonance. It creates an extra stable intermediate. That extra help just doesn't happen with a meta attack. And since the ortho/para pathway has a more stable intermediate, it's lower in energy, and it happens way, way faster.
So here's a quick little cheat sheet. You can see the strongly activating groups like OH, some weaker ones like a methyl group, and then the deactivators. But notice that really weird exception there? The halogens. They are deactivating. They absolutely slow the reaction down, but they still direct to the ortho and para positions. They're kind of the rebels of the group.
All right, now that we have the rules of the game, let's look at the playbook. These are some of the most famous named reactions in chemistry, and they all use the exact same core mechanism we've been talking about.
First up is nitration.
You mix benzene with some nitric and sulfuric acid, and boom, you add a nitro group, negative NO2. And this isn't just some boring textbook reaction, it's a key step in making everything from vibrant dyes to explosives like TNT.
Next on the list is halogenation. Now, if you want to add a chlorine or bromine, the halogen itself isn't quite strong enough to do the job alone. It needs help from a catalyst, usually a Lewis acid. You can think of the catalyst as a hype man, getting the halogen all fired up and turning it into a supercharged electrophile that's finally strong enough to attack that stable ring.
Then we've got the Friedel-Crafts alkylation. This is a fantastic way to add carbon chains to the ring, which is absolutely essential for building more complex molecules. But it does come with a catch. The intermediate carbon chain can sometimes rearrange itself into a more stable structure before it attaches, and that means you don't always get the product you were expecting.
To fix that problem, we have its more reliable cousin, Friedel-Crafts acylation. By adding what's called an acyl group first, we totally avoid those pesky rearrangements. It is a much more controlled, much more predictable way to build up carbon structures on the ring. It's a critical tool, especially in drug synthesis.
So we have the mechanism, we have the directing rules, and we have a whole playbook of reactions. Now for the payoff. This is how chemists take all this knowledge and become molecular architects.
And this leads to maybe the most crucial point of synthesis. The order of operations is everything. It's not just about what ingredients you use, but the sequence you use them in. Adding group A, then group B might create a life-saving drug. But adding group B, then group A could create something totally useless or even dangerous.
Okay, just look at pathway A. We start by adding a bromine. Now remember our rules? Bromine is one of those rebel deactivators, but it's an ortho-para director. So when we do a nitration as our second step, that new nitro group is directed to the ortho and para positions. Now, let's just flip the script. Look at pathway B. This time, we start with the nitration. A nitro group is a strong deactivator and it is a meta director. So now when we add the bromine, it is forced to go to the meta position. We use the exact same ingredients, but a completely different order, and we made a completely different molecule. That right there is the power of synthesis.
And really, this is the big takeaway. It's like having a blueprint for building molecules. By understanding these directing effects, chemists can plan out a multi-step synthesis to build incredibly complex things. Pharmaceuticals, polymers, advanced materials, all with amazing precision.
Ultimately, this isn't just about abstract rules on a page. It's about the power to predict and to design. This knowledge transforms chemistry from a process of just discovering what's out there and to a process of invention. So the question I want to leave you with is this. If you hold the blueprint for these fundamental building blocks, what could you design next?